joint displacements and member end forces or element stresses. But in internal force is strictly speaking, stresses develop. From force, stress can be computed stresses and member end forces or interplane as shown below. Shown below. As already given E equals GPA and 600. Is the Truss problem. Of course, it is easy for finding the member and forces. It is easy. There's only one joint. You can compare it. Just for explaining procedure, I have taken simple problem. Because as per syllabus, it says degrees of freedom not more than 3. Of course, it satisfies that. Here, degrees of freedom. Of course, in the first step, you will see data. It is 3 degrees of freedom. I cannot just take a problem having more degrees of freedom than that. So this is the only problem which I can think of as per syllabus. Otherwise, in practice, you will have any number of these things. So this is mainly we are dealing with finite element approach also. So procedure we are following almost similar. So that's why I am indicating the procedure to start with. Though it is a simple problem, it is all right just to indicate the steps which are involved in the process. So the first step, data or static and kinematic indeterminacy. That's what I have indicated. Static and kinematic indeterminacy. So static indeterminacy with respect to local coordinates, that is PM. Kinematic indeterminacy with respect to global coordinates, that's the displacements. Because here you will see loads are acting only at the joints. So here I is equal to, or M is equal to number of elements or members is equal to 3. So this I will call it as member 1 member 2, member 3. 3 members. Then number of nodes or joints, number of joints 3. 3 joints are there, A, B, C. I will number the joints also. Number of elements. 1, 2, 3. 3 joints. Then choose global axis. So global axis I will choose. Preferably I will choose the global axis such that all members of the given structures are covered in first quadrant, like this. I choose. The global x-axis, global y-axis. So if you want, you can find the coordinates 0, 0, this is 300, 400, 600, 400 with respect to global axis. The coordinates you can identify. That's the data I am explaining. These are all data which are known to you. Then length of each of the elements you can compute. L is equal to length of any element. Li, any element is given by square root of xk minus xk minus xj whole square minus yk minus yj whole square. That is j coordinate, x coordinate of kn, j coordinate of x coordinate of kn, x coordinate of jn whole square, y coordinate of jn. The jn and kn you have to identify. Usually, with that is left to your choice. J to k you can take either from 1 to 3 or 3 to 1. It doesn't matter. So straight away this is a simple problem. Otherwise, in finite element approach, you have to define the nodal coordinates with respect to chosen global, and I have to calculate the geometrical properties of each element, like length, area of cross section, this, like that. So we just say like this: joint information. I can say joint, any joint, I, okay, joint, then x coordinate, y coordinate. You can take it. This is joint 1, x coordinate 0, y coordinate 0, joint 2, x coordinate is 600, y coordinate 300, 400, y coordinate 0. Then 3, x coordinate 300, y coordinate 400. Correct? As per this, then element information. Element information. It's the element I. First element, second element, third element. Element information. Then node J, node K. For element 1, node J, I can take it as node 1, node K, I can take it as 3 or 2. For second element, node J 1, node K 3, then 2, 3, or 3. Here the problem comes, inclined member. Whether I can take 3 to 2, 2 to 3. 1 to 3, 1 to 2, from origin I am taking, there won't be any problem. But other members which are coming into picture, there, which you have to take note, which you have to take this, that is left to your choice. You can take it like this, in any way. Note, that is numbering of nodes that I will take up in finite element procedure. That itself is this idealization of this or discretization of element itself is a big topic in finite element approach. Here in classical this thing we don't have to worry. Just all this information also I need not give because it is same procedure for both finite element. I am giving this, right? Because the first data, it is common for all. That's why I am taking this. Node J, and then N, then direction cosines, then this much information, and of course A also, area of cross section, then direction cosine. Because it's a plain Truss problem, AE by L we have to calculate for all the elements. So that's why that information here, of course, it is constant. I need not have to bother, but we can prepare the data in this fashion. So area of cross section, it is given 600 millimeters square, 600 millimeters square, 600 millimeters square. It is same. And length, I have given the formula xk minus xj, that is x2 minus x1. I have given you the formula, you see. It will be computed in the computer as it is inbuilt for elements I equals 1 to m. But here I am explaining the procedure. So here node j, node k. Here x coordinate of k, x coordinate of j. So that is x2 minus x1. x2 minus x1. 600 minus 0. 600 minus 0. This is x2. x1 is 0. 600 minus 0. That is 600 square. Then yk minus yj. 0 minus 0 square. So that is 600 minus 0 square plus 0 minus 0 square. That square root is 600. So that is straight away no. In classical approach, I can straight away take 6 meters. But I am explaining the procedure, that is 600 millimeters. Then element 2 on same length. For calculating the length, that is x3 minus x1. x3 minus x1. 300 minus 0 square. 300 minus 0 square. Then y3 minus y1. 400 minus 0 square. From this. xk minus xj, yk minus yj. For second element, j end is 1, k end is 3. So x3 minus x1 square, y3 minus y1 square. x3 minus x1 square, y3 minus y1 square. Here I am showing, but in computer you can feed it xi, xk, explaining ik, everything. I and j and in this fashion, automatically it will be computed. So 6 square plus 4 square, that's square root. That is 36 plus 60, that's 500 millimeters. Naturally, this is 3, this is 4. 300, 400. Square root of 3 square plus 4 square. Right? That is 9 plus 16, 25. Square root of 25 is 5. That's 0, 0. Then similarly 3. Third element, it is same as that 2. Otherwise, we can use that formula. That is 2, 3. J end is 2, K end is 3, J K end is your local axis. J end to K end. So that is x3 minus x2 square, y3 minus y2 square, x3 minus x2 square, 300 minus 600 square, that is 900. Yk minus this 400 minus 0, right? So that is 400 square, that is 60. Here it is 3 square, 9, that is 16, 25, it is same as 500. Then N. How to find N and M? There are two ways. They can give in the problem theta directly, or like this they can give. If they give theta, then you know N is direction cosine, cos theta, Y is sin theta, we can calculate it. Otherwise, we can use this formula, L is xk minus xk divided by N, M is yk minus yj divided by N. This is cos theta, this is sin theta. This is cos theta, this is sin theta. You can use that formula for calculating L and M. Here, for first element, xk minus xj, that is x2 minus x1, x2 minus x1, 600 divided by L, 600, that is 1. Naturally, this is horizontal member, theta is 0, cos 0 is 1. Automatically you will get it. Similarly, M is yj minus yj, that is y2 minus y1, y2 minus y1, 0, minus 0, it is 0. M is 0. For first element, L is 1, M is 0. Naturally, for all horizontal members, always direction cosine. Cos theta is 1, sin theta is 0. Likewise, for vertical members, it is 0, 1. Cos theta is 0, sin theta is 1 for vertical. For inclined members, you have to work out from this one. For this member 2, it is x3 minus x1. x3 minus x1, 300 minus 0, it is 300. 300 by 500, that is 0.6. Y is y3 minus y1, this minus y3 minus y1, that is 400 minus 0, 400 divided by 500, it is 0.8. L and M. Like that, third element also, x3 minus x2, 300 minus 0, it is 0.6. Minus 0.6. 300 minus 600. So minus 300 by this. It is very important. Direction cosine is minus 0.6. For this, it is x. That's why I told you, local coordinate to be always from I to j, or j into kn. That is very important. This entire information, first step, it is common for both approaches. Others are all very simple. It is, you can do it. But first step, feeding the data, geometrical properties to be fed perfectly in the problem, or to be worked out perfectly in the problem. It is common for both methods. I hope I made the things clear. Likewise for this, y3 minus y2, y3 minus y2, 400 minus 0, 400 divided by 500, 0.8. Only for this third element, L is negative, rest this. So this much information you have to work out. Then you have to just generate PM and DM, and also degrees of freedom. So that also you have to work out. That's also another important aspect. So having worked out this, these are purely geometry. You have to find the static and kinematic indeterminacy. Of course, straight away all these I could have avoided. I could have started this to start with, because these are all known quantities. I need not explain it. It's all known, having selected a global axis. But I have explained. I have taken time only to explain this. It's all right. So this is this. So here, PM, always in each member, I have to find the member and force. It will be only one force per member. It is because it is a plane truss, only the force will be, internal force will be either tension or compression. It's a tensile force, always we mark the tensile force with end arrows like that. Tension, arrow moving away from the joint. So this is PM1, force in the member 1. Similarly, force in the member in local coordinate, it has to be like this, PM2. So force in member 1, force in member 2, element 2, force in element 3. It is PM3. This is what we have to determine. Member and react or stresses or forces which are developed in the member. Since it's a plane truss member, there will be only one axial force, I told you. That's why while determining static indeterminacy equation, I told I is equal to m plus or minus 2j. M is the force in one member, any member. So if there are three members, 3 into 1, 3m internal forces. Or support reactions, so 1, 2, 3. So 3 support reactions. 2 here, horizontal vertical reactions, vertical reaction, 3m plus r, 3m plus r is 3 plus 3, 6. 2j, 1, 2, 3 joints, 2 into 3, 6. 6 minus 6, 0. That is the determinate structure. That's why I told you it is a very simple thing. That's what I am determining here. Static and kinematic indeterminacy. Right? Static indeterminacy is m plus or minus 2j. M is number of unknown forces. That's only one force per member I showed. Axial force. This is what I have to determine. So this is your PM. PM vector is PM1, PM2, PM3. It's a 3 by 1 vector. That's what we have to determine. Right? Next, another is global. So this is local coordinates. Next, global coordinates. Global coordinates are like this. At each joint, global coordinates will look like this. Correct? Here for each element, local coordinates are like this. At this end, because while deriving this displacement, if you remember, I have taken like this, even now also I showed like this. Arrow moving away. Here, arrow moving away. Here, arrow moving away means in the member, inside, it should be like this. That's why I have taken positive force, member force in this fashion. Because while deriving the stiffness matrix, I have taken local coordinate like this, like this. This and this they are one and the same. Arrow moves away, that's tension. So tensile force, either you can indicate it like this, tension, or in this fashion, as I have shown. Both are same, tension. Compression means arrow moving towards. In any truss member, there will be only one force per member. This is what you have to determine. Global coordinates, mainly displacement, are to formulate ds matrix, right? Displacement. So here you have a hinge support, here roller support. Here static indeterminacy I have told, no kinematic indeterminacy I am telling. Here, since it is hinge, boundary condition, both displacements are zero. Generally, at all joints you have 2 degrees of freedom, truss. Only 2 I told, that is U, J, V, J. M is not there, that's why I have marked. That sketch you have to remember. For general, all the 3 types of structures I have given shown there. Here, whatever is required, that only you have to take. Plain truss, only 2 displacements. Member forces, only 1 member forces. This is very important, identifying the unknowns. This is what we are determining during analysis. PM and displacements. That's what I have taken. Find the unknown joint displacements. And member end forces. Member end forces, local coordinates. Displacements, joints, global. Loads will be in global. This should be very, very clear in your mind. Though it is very simple or don't forget it. Have it in mind. What is that? Very first step we are doing. It is common for both procedure. The finite element as well as classical. It is same. There is nothing here. This you have to understand very well. And you will never go wrong in computation. Otherwise you will go wrong in your computation. You will forget elsewhere. Next, ds. This is 0. Likewise here, it is roller. I have indicated the boundary conditions. This is there. This is not there. 0. Here, both are there. It's a general pin joint, no support condition, nothing. So, degrees of freedom 1, 2, 3. That is your static indeterminacy. Number of unknown possible forces. 3 possible forces. 2 horizontal translation, 1 vertical translation. So kinematic indeterminacy 3. That's what I am doing. All basic concept you should be very clear. Local coordinate, global coordinate, kinematic indeterminacy, static indeterminacy. Now question of degrees of freedom. Degrees of freedom is this. Totally there are 6 degrees of freedom in this structure. Out of 6, because of boundary conditions, 3 are gone. Hinged support, this boundary conditions important. And general compatibility condition is applied. And equilibrium condition I will use in step 3 or 4, formulation of equation. So all conditions also satisfied. All the basic concepts I have explained in lecture 1, all utilized. There you are not supposed to forget that basic concept. It's a must. Everything is coming here. So 1, 2, 3. So this I will call it as what is the joint? This is joint 1, this is joint 2, joint 3. I will call this as a joint 2, U2. This is U3, this is V3. So you got ds is U2, U3, V3. It is 3 by 1. So this much information, though it took time, our basic concept I have explained. This I took some time. It doesn't matter, because these are all the basic knowledge. for both the methods. You have to remember. That is this. Pm vector, ds vector. This is the unknowns. You have to determine. Clear? Unknown standard notation. First step is over. You have to know what should be, you have to determine. And of course, that support reactions, that to be determined, automatically it will take care of that. So the moment I have determined these unknown member and forces, support reactions can be determined after arriving at the main unknowns. And next, second step. Step 2. What is that? Step 2, element stiffness matrix. Element stiffness matrix Km. I have to generate element stiffness matrix. First step is very important. It comes in all the problems. It takes care of both classical as well as finite element approach. When they ask you to solve the problem by finite element approach also, this step remains same. All the science steps remain same, even in finite element procedure. That's why I am taking more time to explain both the things. Only some places we are adopting shortcut procedure, that's all, in classical element. Otherwise, it is same in both procedures. But this is very important. Joint informations, member information, selection of axis, global axis especially. And generating the matrix is what you have to determine. Its order, 3 by 1, 6 by 1. That. So here you will get the idea of maximum indeterminacy. Here you see indeterminacy is 3. In syllabus it says 3 degrees of freedom, 3 unknowns, maximum. So this problem though very simple for hand computation. By classical procedure I can just take, apply equations of equilibrium and solve it in 5 minutes. This problem, after finding the reaction. But explaining the procedure is all right. I have taken a problem with maximum 3 degrees of freedom. It takes time, it doesn't matter, because it is not suitable for simple problems. It's all suitable for the complicated problems, especially using computers. So the procedure which I am following will explain. Second step, element stiffness matrix. So already I told you derived element stiffness matrix for Truss element AE by L to this one. And in the element information, you can find out one more column, AE by L also. Because here only you will have